working hard all day from 10 to 19 over some hours. Just a little tired, but I'd like to start calculating OTA input referred noise, V noise in squared average bar. OTA or operational transconductance amplifier with current mirror, ideal current mirror amps, differential current mirror amp, active current mirror, and differential input and current source ISS. This is M1, this is M2, this is M3, and this is M4. This is P channel and M channel, and this is VDD. And this is output, V out. V1 and V2. And what we need to know is what is the output resistance, impedance, and what is the conductance, GM, of this circuit, and GM all out equals the voltage gain. We can use this lemma, and after knowing this and in parallel and knowing the output noise V and out squared bar, and divided by this AB squared, we can derive this input referred noise representation, Vn in squared bar in volt square per hertz. Remember, volt square per hertz is power spectrum per 1 hertz, and if V square hertz is integrated with delta F, and this cancelled, and divided by R, it's output power, but a noise power, average noise power, and square root of this is RMS noise power in watt, but volts per hertz is joule energy per hertz, energy second. Hertz is 1 over S, volt squared is volt squared, R out is R out, what is joule equal joule per watt second, joule, this is what is joule? 4kT, some for example 4kT-R is a resistance, the noise power of resistance, resistivity R, and which is volt square per hertz, and this is noise power, but yeah, and kT equal joule. Sorry, kT equal in joule. The KTR KTR is this. this equals joule, KTR times R times joule. Okay, T equals joules and times, and hertz per 1 over S. 1 over S when 1 over S cancelled, this is volt squared and divided by R. When divided by R, 4kT equals actual power watt, should be watt. A little complicated. But, so next time I'd like to try again this dimensional analytics, but this time I hold on about this. But we remember volt scale per hertz for noise power, average noise power, and this is a method. Now, how to VN outscale bar calculate is to know this IP noise squared bar and this IN noise squared bar, P channel N channel times R out equals this, and this IP M4, this is GM3 and GM4 and GM1 and GM2 respectively, and GM4 nearly usually equal to current meter, active current meter, and all MOSFETs are in saturation area. Activated in saturation mode, and GM1 equals GM3. On condition of these, INP squared bar is 4kT gamma GM 4 or 3, and looking at M3, which is diode connected, and the resistance looking into the drain of this M3 is 1 over GM3. 1 over GM3 resistance times this current, this 4kT gamma GM 3 current times R equals this gate voltage, and this IPN noise, P channel noise current is added to this is voltage, and this times GM4 squared, because GM4 V in equals this current in linear representation, like that, the same as this, and the current noise added must be added if GM4 V in, and power which is written in power GM4 squared times this, and GM4 and GM3 equal. This is 4 and this is 4, and GM4 squared cancelled, so this is added, so 4kT gamma 2 GM4. So this is 4KT gamma 2 times 2 GM4. And for the other side of NMOS, IN squared bar is what? Input referred for lemma we know from Razavi textbook. Gate input referred current voltage noise from current noise is 4KT gamma over GM1 or GM2. GM1 equals GM2. GM1, GM2. So this is 2 so. This voltage is input noise, gate reference noise, gate referenced current noise, gate noise and this is power, current power, and that makes this current noise input noise, and GM1 squared is falling back to this current noise, and this is 4KT gamma GM1. Just 4KT gamma GM1, but this current is added also for M2 from M1. M1 generates the same amount of current, and this is mirrored through M3 and M4 and appears in here. So this itself, M2 itself, and the mirror of M1 of these current, this value is summed. So this is also 4KT gamma 2 GM1. And noise power is added to node V out. This and this is non-correlated and added up to the all IN out squared bar. This plus this on condition of these conductance equation. And next I'd like to recalculate the output impedance from the small signal equivalent circuit of this OTA, but this time I show that the output resistance approximately equal RO4 in parallel with RO1, RO1 or 3 or 1 or 2, 3 or 4. Looking at this branch, RO2 and RO4, or RO1, RO3. Like this, RO1 equal RO2 and RO3 equal RO4. And the output approximately output resistance is this. Because of the the derivation of or my derivation after this, and this is R out. So this squared times this squared is Vn out squared bar, and divided AVGM R out. R out same this. Divided GM R out, we can get this input referred noise of OTA. So I'd like to memorize this. Equal this here, this here, this here, this and this, or this, or this and this, or this is this and this. This is really equals. This is equals what is 4kt gamma all over times 2gm 4 1 and 4 1 and 4 or 2 and 4. Okay, here 1 equals 2, so 2 plus 2gm 4 or 1 3. This is current, noise current power added up, and times RO2 in parallel with RO, for small character, and then I can check and re-derive this out, and also GM approximately from small signal equivalence, like presented in this textbook. Oh, yeah. And, we know this, and what's the R out and GM from small signal equivalent. Because V in is small signal, and for simplicity, for M1, half V in, the differential voltage V in of half V in is for M1, applied for M1, and current mirrored VDD, and minus V in over 2 will be applied in M2, and for conductance, the current here is GM1 win, and the current here equals minus GM2 equals GM1 win, but the direction is this is positive, this is negative, so this whole direction, and this current I out is in this direction for node output node, and this current is mirrored to here. This current is same as this small signal, and this is mirrored to this small signal. So this directional positive GM1 of V in plus this direction of positive GM1 win over 2 is added up to this node, output node, to GM B in. So I out equals GM V in minus, because the direction is different. So transconduction GM is approximately in here. The absolute value is GM1 in here. GM1 equals GM2, represented by GM1. So here we know this time approximately capital GM equals GM1. So GM1 divided by GM1 R out R squared, is input referred voltage noise power average in volt squared per hertz. And what is R out? And this, from here, small signal, this is AC constant or opened, because this is no variation appears here. So, and this current, this is equivalent to us this, but AC ground, and this is IX, and this is Vx. External voltage is applied to V out, and looking into the V out, resistance is R out, and the resistance R out Vx over Ix, and which is Ix. This Ix in part this direction, Vx, this is Vx over this resistance, this path is I1, and this part I2. Ix equal I1 plus I2, or Vx over I1 plus I2 equals this total Ix equals R out, and this is RO2 and this is RO1 in saturation. So different direction from equivalent voltage plus half V in and minus half V in generates different current direction, increase and decrease. This is decrease, so inverse direction, this is increase, or vice versa, and the current is always in or up or in. So we actually applied this direction increase, also this direction decrease, so the current AC current direction is the same through this VP common drain current mirror NMOS drain node, which is open for small signal equivalence. This I1 is through RO1 in series with RO2, so RO1 plus RO2 equal to RO1. And this is equivalent to Vx applied, and this resistance is 1 over GM3 in parallel with RO3. actually. And this is to AC ground. So the Vx over 2RO. So we need some other space. Vx over 2RO1 plus 1 over GM in parallel with RO3 is one part, and the other part is this voltage is to gate of M1, 2, 3, M4, and M4 driven by, and this current so 2RO1 plus 1 over GM 3 in parallel with RO3. This current times this current times this current is this is gate, this is current, this current times 1 over GM3 in parallel RO3 is gate voltage of this M3, and this gate voltage here RO4 equal RO3, RO4 in parallel, and this current, here's another one more current, I3 equal plus Vx over RO4 equal RO3, and this current and this current plus this resistance, gate resistance times GM4 equal GM3. This current plus this current is here, and this current is here, and this current is here, and this current is here. So this added up, all added up to this. Okay. So adding all these, simplicity 1 plus GM3 1 over GM3 in parallel RO3, this current plus this voltage GM, this gate voltage, this current, plus Vx over RO4 equal RO3 equals the total I out, Ix divided by, so Ix divided by Vx equals the Vx disappeared, and here the approximation is applied. 2RO1 is much larger than 1 over GM3 in parallel RO3, and also 1 over GM3 is very small, relatively very small, smaller than relatively very smaller than out of 3. This is nearly equal to 1 over GM3, and this is nearly equal to 1, so this is nearly equal to 2, and this is very small, so this is neglected, and this 2 is cancelled out, so the left side is remain left side is this plus this. What is this? This is that R1 in parallel with R3. This is approximation. Equals 2R1 several kilo ohms, more than several kilo ohms, much greater than 1 over GM3 in parallel R3, which is approximately 1 over GM3, and so many things cancelled out, and the Ix over Vx equal approximately R1 in parallel R3, R1 in parallel R3, or R2 in parallel 4. This is R out. So GM equal GM squared, GM1 squared, R out equal R1 in parallel R3 squared. This is voltage gain power, and this cancelled out, and GM4 is GM3, GM2 is GM1, and so if we raise again this, finally input refers voltage noise power average in per hertz equals, finally we can get the useful expression formula for KT gamma GM1 GM3. 2 is outside, 8 times 2 times 4 is 8, and into GM1 squared 1 over GM1 plus GM3 divided by GM1 squared. Is Vn in squared bar of OTA, differential OTA GM1. Input to deferred noise of OTA is given by transconductance of M1 and M3. So to get smaller input refer OTA voltage, we need to minimize the active current meter transconductance of GM3 or GM4, and we need to maximize input MOSFET transconductance GM1 or GM2. This is it. This is tonight. Tired daily dummies trial for CMOS Analog. It's all for today. Next time, I'd like to deliver the input referred noise for source floor, and again common source amplifier and source floor, which is very useful. I know both are written in CMOS textbooks. I'd like to, by myself, for me, for my own sake, recalculate, deliver the expression of these input referred noise of these circuits. Common CS and SF, source follower. Single end, both single end. This is single end differential input operational transconductance amplifier for OTA. And I'd like to also why volt per hertz equal 4 kT R for resistor, and KT is in joule energy, because freedom over 3 kinetic energy in the mass averaged per unit molecule equals 3/2 kT. This is kT equal energy. Boltzmann constant maybe 3.2331, 8.31 times 10 to the minus 23. no, 23 more, 23, 21, 23. Oh, I forgot. Boltzmann constant and temperature in Kelvin. Sorry, I forgot K value. Then 22, 21 or 23. 23 molecule. 3 volt. Avogadro number is 6.22 times 10 to the minus 23. 8.31 times 10 to the minus joule per Kelvin. Minus 23. Minus 20 something. And this is joule, but 4 kTr is volt square per hertz, and time multiplied by delta F frequency. It's average voltage power, but actual voltage power is must be divided by R, V square over R. So this is 4 kT. 4 kT equal watt in watt, but 4 kT times frequency is watt. 4 kT times frequency is watt. 4 kT times frequency and divided by R. This is watt. Actual power, volt per ohm. Volt per ohm. V square over R is watt in watt. In a usual manner. So 4 kT delta F equal watt equal joule second. It is joule second. And 4 kT equal joule. But what? Joule second. What? Joule per second. Okay. There's no contradiction. Watt equal joule per second, sorry. Joule per second equals Joule delta F per second. KT equals Joule energy, molecular energy, nearly in three-dimensional space, one molecule KT, and 4 times KT, Joule times delta F, 1 over F. So Joule per second, this is watt. And times R is, and divided by F is volt square per hertz, represented by for voltage noise generated by resistance R. This is not actual power. This is not actual thermal power or thermal energy in unit time. So take care. Just for get voltage and squared RM's value, we can get from this, and squared all over squared we can get RMS value of the noise after integrated some bandwidth. Noise in what rate, to what extent, from within what frequency range the noise is transferred, can be transferred through this amp. So amplitude cutoff frequency may be 0 to some cutoff frequency delta F is multiplied by this, and all the noise of noise power is in volt squared, and square root of these we can get RM's value in volt, namely sometimes in usual case microvolts, hundreds microvolts, several hundred microvolts of RMS value, and which is actually observable using oscilloscope. Some fluctuation, peak to peak values in several hundred microvolt for RMS. In RMS, and the calculation from calculated output of the RMS value several hundred microvolt is this noise voltage power times bandwidth all over squared given by this, we can get RMS value. This is voltage. So 4kTr or 4kT gamma GM is not just thermal power, thermal energy. You can recheck the dimension analysis using KT, knowing KT equal in Joule, and power is in watt. Watt equals Joule per second, and frequency hertz equals 1 over F. Using these, without no contradiction, you can remember more correctly. This is for voltage RMS noise, power spectrum per unit hertz. This is per unit hertz, and no square root. Of course, this is the finally given OTA input referred noise. This is input referred noise. Input referred noise is for any fair for any voltage gain amplifiers. Output noise depends on the voltage. Output noise generated by its own generated by the amplifier itself is depends on voltage gain, but the output noise divided by AB, which is input referred noise, is fair comparison or fair comparative noise value. So we usually use input referred noise like this. Input refers common for any gain amplifiers. Any amplifiers of many amplifiers of any gain. It's fairly compared using input referred noise, not output noise, which depends on voltage gain. Gains larger, noises at the same time much larger. If gain is small, noise is small. In looking to the output, but input referred noise doesn't depend on amplifiers voltage gain, but we can never know. Usually we can never know the input referred noise. So the virtual comparatively very fair reference for noise of amplifiers, which is input referred noise. This is for OTA calculated today. Oh, it's too late. But which 11? Oh, it's 11 at night, 23 o'clock in Japan. So I need to go to bed in an hour. But are there anything I'd like to record or remember for this topic? Okay. Next time, CSCF, input referred voltage noise. Of course, redelivering delivering the amplifier voltage gains for each of CS and CSF. Of course, using small signal equivalence and using Thevenin Norton equivalence. A very simple method using presented textbook, we know, but a little bit difficult, not easy to understand the description story of the textbook, but just put some thoughts, we can well understand of these topics. So daily dummies, fair trial for CMOS Analog is continued. I don't know. If continued, tomorrow night I'd like to try CS and SF. Good night.